Okay, so good morning. Let me start now. So basically, in the first lecture, we saw the wide frequency spectrum and why we should go to high frequencies because your large bandwidth is available and so on. And then we discussed about the communication system. Uh, Basically, we discussed there are properties like there are problems like noise, interference, distortion, which I put in one category, noise itself. But dictionary meaning, if I see, they are one and the same thing, unwanted signal. And we understood what is a signal, analog signal, digital signal, and so on. And today we'll understand slightly this signal in much better form. So as we have seen in the previous lecture, our communication system, uh, which we are going to discuss, uh, has various elements. So suppose I got some source, let's say I'm speaking. So that becomes my input signal. And it goes to some sort of a input transducer because my speech is very random. Uh, so I need a transducer to convert one form of energy into another form of energy. And then basically I am converting my speech signal or acoustic signal to an electrical signal. So because then only I can transmit through a transmitter. So it goes to a transmitter, which is the main element. And then it goes to uh, a communication channel. As I said, this communication channel could be anything. It is wireless, it is wired or copper wire, and or it is fiber optic. So three forms of communication is there. Either it is a wired, which is what we call the landline, or wireless, or fiber optic communication. And all the three communications were there and going to be there in future also. Okay, because we are dependent on all the three. Each has its own advantage and disadvantage and so on. And then it goes to the receiver. Receiver is basically, it receives the signal. So this, after this, you get a transmitter signal, which we normally write as transmitter, and receiver we write as a receiver. And this receiver signal is basically goes to the another output transducer, because you will not, when I'm speaking, it has to be in the same form at the receiver end. You can't, if I'm speaking a speech, you can't understand if I just transmit in the electrical signal form, okay, voltage or current. So I need another transducer here, which is an output signal. And then we get an output signal here, which goes to the what we call the destination. So this becomes my transmitter, this thing. And in these three systems, basically your transmitter is very important, your receiver is very important. Other thing is transducer, and other thing is just conversion of, and your communication channel. Now, when we go to the communication channel, especially in the wireless, which is quite important here, which is a noise could be added, interference is added, and distortion is added. So that's what we discussed last time. And this basically reduces my receiver signal strength to a larger extent. So these are the three basic problems as we have seen: noise, interference, distortion. And the two fundamental limitations, basically what we have also understood in my last lecture. I will share those slides with you very shortly once I get the exit list of the students enrolled in section B and so on. So still I'm waiting for that. I think probably this week we'll get it. And then I will share my previous lecture notes also with you. So this is my communication system. Now here, as we have discussed last time, the two important things for us is basically in a communication system is the bandwidth or important resources and power. So to understand this, how important is the bandwidth, we define with regard to what we call channel capacity theorem, which is what is given by Shannon's law. So what is this Shannon's law? So as you discussed, it is what we call the Shannon's law. Please ignore what we spoke in the last lecture about the Shannon. There was slight error. I will explain to you. because that time my network got disturbed and I slightly missed that point. But when I saw the notes, I found there is a slight mistake there. So it is called the Shannon-Hartley theorem or Shannon's law, simply because he was the main contributor. And basically, it is for defining the channel capacity, the channel that we have discussed between the transmitter and the receiver, how much signal could be transmitted. Because nowadays we say 100 Mbps data, 200 Mbps data, 500 Mbps data, and so on. So how much maximum I can transmit? Like if you are a subscriber to Jio, they ask you how much data speed you want. And according the cost is higher. Okay, because a larger speed, larger channel capacity means large bandwidth is required, and the operator has to pay a huge amount of money to buy that bandwidth and so on. And obviously, they have to get it from the consumer. So here, the channel capacity is of a channel is given as what we call C is equal to. Please note that there was a small mistake. It is a log to the base 2. I just forgot to write to the base 2, 1 plus SYN. So this is given as, and it is given in BPS. When we say kilo BPS, MBPP, megabits per second, and so on. So it is given as bits per second. So that defines my channel capacity, which could be in kilo or mega. And we today nowadays we always prefer megabits per second because kilobits per second our data speed will be very slow. So the unit for channel capacity is given as this one. B is C of bandwidth. B is bandwidth, which is typically given in terms of hertz. And S is the signal, and N is the noise power or noise voltage. So suppose my, because this is in terms of log 2, which we are not comfortable, log to the base 2. So please note that the last lecture, please ignore that one. Okay. Last lecture, I just forgot to mention log to the base 2, I realized later on. And because log 2, we are not very comfortable, we are comfortable with log n, log to the base 10. We can convert this quantity in terms of the log to the base 10 also. So the channel capacity is given as 3.32 B log to the base 10, 1 plus S by N. Why? Because it is the standard thing which you must be knowing, since your log to M is equal to 3.32 log 10M. So that is the basic mathematical thing we know how to convert a log to the base 2 to the log to the base 10. So this is something is very important. We normally use this thing because we are more comfortable with the this value, log to the base 10. Let's say do an example, because I always prefer to have certain examples based on what we have learned. Just to ensure that, suppose let your bandwidth is something like 3.1 kilohertz, and S by signal is, let's say, I could give something like 1000 millivolt. Noise is basically very small, but even that small noise is very important for us. So that gives me what we call a signal to noise ratio. I told you what is the difference between electronics and electronic communication. It is basically the noise factor that we add. And then I wanted to know what is the channel capacity. So to solve this, I can use this formula. C is equal to 3.32 into B. Now B is, I convert into hertz because B is in hertz. So that becomes my 3000 hertz, and then into log 10, 1 plus, it becomes 1000 by 1. So if I convert this thing, I get the answer is 30,900 BPS or 30.9 kbps. So that is how we define the channel capacity. That means if my
Sir,
band, yes, yes, please, yes.
sir, how do we define a channel capacity?
How?
How do we define channel capacity? What is
Channel
channel?
channel capacity means how, okay, I will put in a definition form in my next slide. This is clear. Channel capacity means, okay, I can define like that. Basically, it is how much data I can transmit, at what speed I can transmit. Okay. So obviously that speed depends upon the bandwidth. Okay. It is, you just understand like this. I will try to give an analogy. If you have a small door, okay, a main door of your house is small, only few persons can go through that. That means the bandwidth is small. And when the few persons go in a very small, through a small door, uh, in a particular time, only few will get transmitted from one inside outside to the inside. Okay. So, but when I increase the bandwidth of my door, I increase the size of my door, many people can go simultaneously. Okay. So it is, channel capacity means it is how, what is the speed? Though we say it is a capacity, it should be in terms of mm, uh, uh, data, how much data I can transmit. But basically, how much data I can transmit is important in a particular time period. So it is defined in terms of basic bits per second or kilobits per second or megabits per second. But whenever we take the unit of bandwidth is in hertz, it is in per second. Okay. Otherwise, if it is in kilobytes, bandwidth is in kilohertz, then it is kbps. But better to convert it to hertz and get the answer in kbps and so on. So channel capacity is simply your how much data I can transmit in a particular instant. Okay, so that is how I define the channel capacity. So my channel is important. Like your copper cable has a very limited bandwidth. That's why we go for fiber optic. Fiber optic has got a very huge bandwidth. But the fiber, the problem is that you are still connected to the cable. Wireless has the capacity between the two, your copper cable and the fiber optic. But wireless, you see the various advantages. You can carry, you can be more mobile and so on. But wireless is very much prone to noise interference and distortion as compared to other signal. Because in copper cable, you have got copper, it is shielded, so there is no external interference. In fiber optic cable, it is also shielded, there is no external interference. But here, when I'm transmitting, a building will come, it will attenuate my signal. My signal will get lost. If it is raining, my signal will get lost. As I said, all these parameters are important, weather parameters and so on. So channel capacity, you simply say it is the how much data I can transmit in a particular instant through that channel. And that channel could be either a wireless, fiber optic, or this thing, a copper cable, which are the three modes of the communication. So this is the, I think we should use 3.32b log 10. But normally, if you see the books, they are defined in terms of log to the base 2. So this is for the easy calculation because we find it easy to work in terms of log to the base 10. And some of the things are very straightforward. Log 10 is 1, log 100 is 2, log 1000 is 3, and so on. Moving further, now, last time we did. Yes, please.
Sir, what is the unit of S and N? It should be
Oh,
volt or volt squared.
it is a ratio. As I said, in this case, in this example, if you see, I have taken a millivolts. I am speaking in terms of millivolts. It could be in terms of milliwatt. It could, so it is a ratio. It is a ratio. So we say S by N is a signal to noise ratio. If you recall, in my last lecture, if you have understood where I have also written there, S by N we call as sometimes as S and R. It is what we call as, so it is a ratio, signal to noise ratio. Okay. So it has no units. It has no units. And don't confuse with that. If it is no units and the bandwidth has a unit of hertz, it is fine. That is basically your bandwidth is related to the how many bits could be transferred within that bandwidth in a particular instant. Okay. Now moving further, as we discussed last time, there are two types of the signal. One is what we call the analog, which is like a continuous signal of any waveform. And then we talked about the digital signal, where the signal is in the form of it is also called a pulse signal. Okay. So this is a continuous signal, something like this. It will continuously move in an arbitrary fashion. Okay. Pulse signal is just like a digital signal. So it is in the form of the pulses, something like this. Okay. So it repeats. It is like a on-off signal. So sometimes it is also called a pulse signal, or sometimes it is called a discrete signal. Discrete is the dictionary opposite meaning of continuous, but more commonly known as analog, digital, and so on. Now let's understand what is this signal. This is a very general form of the signals, and initially we'll concentrate on analog part, and then we'll, in this lecture series, if you see, it is called the analog communication and transmission line theory. There is a separate course on the digital communication. Now, in this lecture series, I said that because the name is analog communication, this is very important because yes, we prefer digital signal, which we'll understand why and so on. But basically, our real world is analog. My speech, when I'm speaking, or any signal, it is in the form of an analog signal. And it could be of not only same amplitude and something like this, it could be of various amplitudes, something like this. So that becomes my analog signal. And similarly, my digital signal could be also of various amplitudes and so on. So that becomes my this thing. So if I plot this time versus amplitude, analog signal is like this. And if I plot time versus amplitude, digital signal could be like that. That the amplitudes could not be the same. The frequencies could not be the same. It could be different. Like here, the frequency is changing and so on. So let's understand. Now we concentrate on the analog part. So what is an analog signal? As I said, how to represent an analog signal. So we'll just understand now. This is very, very important. Representation of an analog signal. Now, please note that there are very, very small things which you have to keep in mind. It is written as V as a function of time. So we normally start with in time domain. I think you must have used oscilloscope, or I am very sorry that you could not physically been in the lab, but I think you must have done in basic electronic course oscilloscope. So oscilloscope is a time domain instrument. That means on the x-axis it is time, and y-axis it is the amplitude, which could be in millivolt and volt and current or so. So I could represent an analog signal like this, which I will explain. Vm sine omega m, or simply I would say sine omega t plus theta of phi. Now please note this is what we called amplitude of the signal. Okay, typically it is a DC value. Okay, so it is written in capital letters. It is always written in capital letters. So it has got an amplitude part, and then we have what we call the Vm. Okay. And omega is nothing. It is your 2 pi f. F is your frequency, which is what we call the hertz. Omega is nothing. It is your angular frequency, which we typically denote in terms of radians and so on. Okay, so that becomes my frequency part. And then we have what we call the phase part. And theta is the phase. That means there are three basic components of an analog signal in time domain. And this is what we call a complete signal. So a signal has got an amplitude, it has got a frequency, amplitude, frequency, and a phase. Just for your this thing, I will write in full units. Frequency in hertz. And phase is there again in radians and so on. And amplitude of the signal we define in terms of millivolts, volts, whatever you call, and so on. So these are the units. So the complete signal is characterized by the three parameters. And I'm assuming for the time being a simple sinusoidal signal because when we start, but my signal could not be simply sinusoidal. As I told you in my previous slide, this is not a complete sinusoidal signal, that's one. But this is a proper sinusoidal signal, this one. So, but for simplicity, when we start a course, we assume with the simplicity and then we extend it. So right now we are assuming, and I just think because it is a first lecture course of the communication system, here we always assume to start with a sinusoidal signal. So that's why it is sine. Or it could be represented as like cos also. Don't worry about that if somebody uses cos. Basically, it is a sinusoid signal. So it is a, I would assume that it is a sinusoid signal to start with. Okay, sinusoidal. Okay, so that's why we are putting it in the form of sine or cos omega t phi. So how this thing looks, if I put in a graphical form, in time domain, as I said, in the x-axis it is time, and then in the y-axis it is the amplitude. So here, so this is when we say YVM, VM means peak amplitude, peak or maximum amplitude. Because as we see here, sometimes amplitude is going up, sometimes going down, but it is the maximum peak. So that's why VM here we use. So it is the peak or the maximum amplitude of the signal over a particular time in millivolts, volt, milliampere, ampere, whatever is there. And frequency is nothing. Your frequency is given as 1 by t, the time period. Because when I'm plotting in the time domain, that means time versus amplitude. So I can calculate this thing. And phase angle is a, I can define in the next slide what is this phase angle. Okay, I can write down. And this theta, which is my phase angle, so it is nothing. It is a measure of, I could say, relative position in time within a single time period of sinusoidal signal, because we are speaking in terms of this sinusoidal only. So we also know that 2 pi is nothing. 2 pi radians we can convert into 360 degree. So that's also we know that. So how we see this in a graphical form? So it looks, my signal will look like this. Suppose I plot with respect to omega in terms of radians or time in terms of seconds. Okay, but we normally plot with the time period. So we'll just put it like this. And this I plot in amplitude in volts. Okay, I could have a signal, sinusoidal signal, something like this. There is a positive value and there is a negative value. So this I define as Vm, and this I define as minus Vm, and so on. And this, from this point to this point, because it is in the time, as I said, we normally speak in terms of the time rather than angle. Okay, so I just remove it here just to avoid any confusion. So this becomes my complete time period, because after that my waveform starts getting repeated. So this is the one complete cycle. This is one complete cycle, and this is what we call T, and this is nothing, it is equal to 1 by F. Because the frequency, the unit of time is second, and it is 1 by second per second, that means it is hertz. So that is how so this way we define a simple sinusoidal signal in mathematical form. And this is a time domain. Sometimes as we go in the higher classes, we also look for the frequency domain. That means the frequency versus time, but that we are not talking about right now, which we'll discuss in the later lectures, later course part, and so on. So this is something like this. So suppose I have some signal, which is something like 10 volt and so on. So here, suppose I want to plot a form. Let's take one example. I always prefer to give certain example. Let me take. Normally, to start with, again, most of the time we keep phase as 0. So it is main components for us are amplitude and frequency. And later on, we'll see the frequency and phase are also related to one another. Let's take one example again. Suppose I have to illustrate an analog signal as Vm equal to 10 volt, F equal to 1 Hertz, and theta equal to 0 radians. Okay. Then how I can illustrate this? So my signal will become here Vt is equal to 10 sine 2 pi f is equal to 1 t plus 0. So that becomes my signal. And if I have to represent this signal, either I can ask this way. So it becomes, that means my amplitude is 10 volt. So this is nothing. It is your Vm. And here my f is equal to 1. And this is my theta, which is equal to 0. Okay, so everything is in radians. So here, if I put it in a form, I could plot it like this. I could illustrate like this. So this is my signal T. This is my amplitude in volts. Because when we do the amplitude, we get the signal in some form. So we have to depict it. But we are doing, in the theory, we are doing the other way around. I have given a signal, and now I'm depicting in a figure, which we normally see in an oscilloscope. So here my signal will be like this. So here it is, I would say 10 volts, that is equal to my Vm, okay? And this becomes my minus Vm equal to minus 10 volt. And the time period is 1 second. So here I would say it is 1.0 second, 0.5 second, and so on. So your time period now becomes equal to 1 second from here to here. So that is how we have illustrated. So this becomes my mathematical representation. This represented by graphical representation of this signal. So either from this figure, I can come to this signal in the mathematical form, or from these values, I can come to this signal in mathematical form or an illustrative form. But if I have a 5 volt, let's say instead of Vm equal to 10 volt, I've got 5 volts. So this becomes my 5 volt and minus 5 volt and so on. If I have 2 Hertz signal, then obviously my time period will be halved. Okay. So in that case, it will become 0.05 here and so on. So it will be just how you present the signal in either of these forms that becomes quite important here. And moving further, as I said, we are not talking about the phase part right now. But let's understand how, if there is a phase, also we can take that example again. So suppose I have a signal, something of this form. Vm equal to 10 volt. Frequency, let's say I've taken only same 1 Hertz, but I take theta equal to pi by 4 radians. If I take the theta as pi by 4 radians, then how it will look. Now in this case, my signal could be represented as Vt is equal to 10 sine 2 pi t plus pi by 4. So here it is my Vm, which is in volts. Here it is my frequency, which I have taken as in Hertz again. And this is my theta in radians. How to look for that? Now, if I plot and see, now if I see from the previous one, the only difference is this phase part. Here was my phase was 0. Okay, so I can put it like this to make it clear. So this is how I am getting here. Now, in this case, the only difference is what we have seen here. Let me change this one. It is pi by 4 radians. Everything remains the same. So here, it is the same thing here. If I plot t in second here, And if I plot it versus amplitude in volts here, so it is the same thing here. So I first draw the same thing, but now if you notice here, amplitude goes in the same way, but there is a phase shift of pi by 4. And as I said, time and frequency and phase are related. That also we'll see later to one another, as time and frequency are related to one another. And frequency and phase are also related to one another. Okay. See, phase means there is a delay of the signal. So if you see, the phase is related to time. Why the phase change occurs? Because there is a delay of the signal. When a signal is transmitted, it gets delayed. Why it gets delayed? Because, say, length of the cable is slightly more and so on. And because it is delayed, the signal will start at a different instant. If you see here, the signal start in the previous slide, the signal start exactly at this point, that is t equal to 0. And at t equal to 1, which is the frequency corresponding to 1 hertz, 1 second, it exactly ends there and the new cycle starts. It is a continuous cycle, though I have taken up to one complete cycle here. But this cycle goes on repeating. So this is your one complete cycle, which is what we call the one complete cycle of the wave. And then the cycle repeats. So in the next slide, it is slightly different in the sense that because there is a delay of pi by 4, my signal will not look exactly in the same way what we have seen previously. It will be looking like this. It will be slightly starting at a particular delay, reaching here, and again reaching at the peak here. Again, it will be starting slightly late here, and so on. So basically, if we see here, because there is a delay, and this delay is because of the pi by 4 radians. So I can just see like this. We can't measure it directly here, but yes, there is a delay of the signal. So there is a considerable delay. Earlier, what our peaks were at exactly they start here. Our complete cycle starts here. This and this. Now this is getting delayed, and instead of making it 0 here, there is already some amplitude there. That means signal has already started. There is already a delay. It could be a negative delay. It could be a positive delay. So this becomes a phase shifted signal. So, but as I said, initially we'll assume that the phase is 0. But this is a phase shifted signal. If you could see, if I have to illustrate the two signals. And if I change the frequency to 2 hertz, again, for the time wise, it remains the same. It is 0.5 second here. It is 1.0 second here. 1 minute. This is 0.5. So still the complete cycle, which is from here to here, is remain the same. But we are taking at a different amplitude level. And this is the same here, Vm. And this is the same here, minus Vm. So 10 volt here, minus 10 volt, and 10 volt. So this is how we look for a analog signal in the time domain. As I said, we can go in the frequency domain also. There we go for frequency versus time. And in this case, I have to plot f equal to 1 by 2, which we are not taking into account right now. Moving further, so we have understood how a communication system is there, how the power is getting transmitted, signal is getting transmitted, the communication channel, and so on. Now, as we have seen here, bandwidth is a very important resource. So one we call the communication resources. What the problems we encounter? We have seen last time, it is the noise, interference, distortion, which we'll discuss slightly later when we talk about the noise in detail. But I put in one category. But noise, interference, distortion are 3 different things for us. So primarily the 2 main resources for us is what we call the bandwidth. Another is what we call the power. Because power is very important to us. The larger the power, I can transmit to a larger distance. The smaller the power, I can transmit to a smaller distance. Bandwidth, larger the bandwidth, I can transmit large amount of data. Smaller the bandwidth, I can transmit only a small amount of data. So these are the two main factors what we have seen for a communication channel to go for that. Now coming to the modes of communication. What are the various modes of communication? One is what we call the simplex. So this we are going to start. So first one is what we call the simplex. Now simplex means the information can be sent only in one direction. Okay. So I would write down here. Information can be sent only in one direction. What, for example, what it could be one? Your TV, your radio, all these things. So these are the simplex type of the communication system, because TV means that they are transmitting the signal. The Doordarshan or the any signal is getting transmitted to you. You cannot transmit anything. You can't say that I don't want this and I don't want that. So it is a one-way communication, and that is what we call the simplex communication. Then we have the next one is what we call the half duplex. Sometimes we write as SX also, and sometimes we write as HDX for simplicity, but otherwise it is half duplex. So here, information can be sent in both directions, okay? But only one at a time. So first I will write down here. Information can be sent in both directions, but only so this is important. Simplex, here I can transmit in both directions, but one direction only at a time, like your walkie-talkie. When you know that when you're in walkie-talkie, one person speaks, other listens. Then other person speaks, the first one person listens. So that becomes your example of half duplex. So here I could say the example is your walkie-talkie, which you are very familiar. That is what we call the half duplex communication. Okay. Or that is used by police and all these people that we are aware of. Then we have what we call the full duplex.
Sir,
Yes, 1 minute. FDX.
so telegraph is of which type? Telegraph.
Telegraph is also earlier, it was like a one form of the communication. You are typing the message and so on, and that goes to the other direction. Okay. Both of them could not type one another. Telegraph is like was earlier, if you see that it was a printed form, telegram and all those things. So it was like a one-way communication. Okay. Or you can actually put in the walkie-talkie category, because they are, if somebody responds from there also, but it is like a one-way communication. The other person may respond not immediately, maybe after some time. So telegraphy is no more in there in the picture, as I said. But you can put in the simplest form of the communication. But nobody talks about. But TV, radio, we still talk about. Walkie-talkie, we still talk about. Now, in the full duplex mode, the information can be sent in both directions simultaneously also, not one at a time. So in this case, this is the third form, FDX. So information can be sent in both directions simultaneously. So now you know what is the advantage. What are the examples for this? Obviously, your mobile phone and so on. So this becomes your mobile phone, landline phone. Means you can speak and you can also listen while somebody else is speaking. So this is your all these examples of mobile phone, landline phone are in this category. Sometimes we have the two-way radio, even the satellite communication, even if your like data communication, whatever we talk about, and your LAN, local area networks. All these things is what we call the uh, um, full duplex. Now, there is another category which you will not find in many of the books. They simply talk about simplex, half duplex, and full duplex. There is another category which also we encounter in some of the recent books and so on, and that is what we call the full duplex, or sometimes it is written as FFDX. What is full duplex means? Again, data transmission is possible in both directions at the same time, but not necessarily between the two stations. Okay. Full duplex means like your phone. You can listen with the other person. You can also speak to the other person. Full duplex means, so I could say communication in both directions at the same time. Obviously, full duplex is same time, but not between the same two stations. Like what we do the conference call. It is a full duplex mode. I am not speaking just to two of the people. There are many people are there in a conference. So that becomes your, so it is like a multi-point communication link. So it is your multi-point communication link, like your conference call and so on. It comes in this category. So you may be speaking, third person may be also speaking, second person may be listening, or all three of them speaking and listening. So that is what we call the full duplex mode of the transmission. But mainly it comes in the category of the duplex. So sometimes many books treat as a part of the duplex only, and sometimes they treat as part of the, they treat as separately as full duplex signal and so on. So this is about this thing. Then comes to the, because we are talking about the analog signal, let's understand a little bit about the, though we are going to have a separate lecture series on that, we also speak about the digital communication, little bit of that. So here my analog signal need to be coded. So I need to code, say I need to code in the form of zeros and ones and so on, pulse. So what we do here in the digital transmission or the digital communication, though as I said is a separate course, but because we have given the word here, we have to little bit understand about that. Okay. In the analog communication, what you see, there was an analog data, voice. It goes over a telephone, and then it goes into to the receiver, at the other end in analog form. Okay, analog electric signal, analog voice signal, and so on. But in a digital communication system, you have to use some sort of a coding. So here we do what we call the coding. So basically, what is this coding? Coding is nothing. It is a I would define as some symbol processing. Symbol processing means I give them a code. Suppose I have a signal, something like this, an analog signal like this. I try to sample them. I try to code them that whenever it is greater than 5 volts, say plus 5 volt, 0 volt, and so on. When it is greater than 5 volt, I say it is 1 or on. When it is less than 5 volt, I would treat as 0 or off. So I can convert this analog signal into a digital signal in some symbols or some digits. These are called the binary digits. Okay, bits. So this is also called the bits or binary digits. Now here, so I could say, I could classify wherever my signal is greater than 5 volt or greater than say, sorry, in this case it is 0, minus 5 volt and so on. So if I say it is 0 to 5 volt, Sorry. So this was my analog signal. This was my analog signal. So I want to symbolize them. I want to code them for digital communication. So if I say 0 to 5 volt, and here it is 0 to minus 5 volt, I code them as 1 and 0. So in this case, my signal will become like this. Here it will become 1, here it will become 0, it will become 1, it will become 0, and so on, corresponding to the same time period. If I see this time period like this. Okay. So this is what we call the coding. So here, if I plot again with the respect to the time, it is time again here, it is time again here, and this amplitude again here as we have done previously. And this is also amplitude. So basically, I'm able to convert a signal into a coding form. So it is not a continuous signal. Now it will become a discrete signal. Sometimes we say it is an on signal, off signal, on signal, off signal, and so on. So digital communication has its own advantage, and we'll just see later on what are the advantages. But this is the very basic, that you are coding it. And when you're coding it, it could be in this fashion, or there are many ways to code it and so on. And once you code it, you have to decode it also at later on. So this is the example of a what we call the digital communication and coding and this thing. And for that, we do some sampling. This is also called some sort of a sampling also, that you are sampling the signal at a frequent time periods, at some time periods. Now, coming to the next part. So these were the almost all the basics that we have learned so far for regard to the communication point of view. Now we'll understand slightly the next part of the series, and which is what we call the modulation. Now, modulation, if you see the dictionary meaning, so this is a new chapter I'm starting. What we call the modulation. And this is something like we have to be very, very careful in understanding. And I will try to give analogies in our day-to-day life so that what is the advantage of this thing, modulation. Why the modulation? So if I look for the dictionary meaning, Oxford dictionary meaning, as I said, most of the times when we use the technical words, they are nothing. They are actually the simple Oxford dictionary words. Sometimes we use a more technical word for that, like loss of a signal is an Oxford dictionary. But in communication language, we use the word attenuation rather than the loss. So, but it means the same thing. Even nowadays, you will find attenuate as an Oxford dictionary word, which is quite common. So if I see the definition of or meaning of a modulate in dictionary, it means to change. What I should change and why I should change. That is not something. So this is the dictionary meaning. So if I have to define what is modulation, modulation I could define as, I'm writing each and everything for you also. It is the nothing. It is a process of changing one characteristic or parameter, whatever you call, of a high frequency signal or carrier signal. First I'm writing and then explain to you. In accordance with message or low frequency, or I would say intelligence signal at any instant, or I would say instantaneous value. Instantaneous value, we always value of time. Now, what it means? See, my signal, let's say my speech signal. A speech signal, as you have seen, it is a voice frequency. It is a low frequency signal. Now, if I want to transmit to you over a large distance, okay, I need some sort of an antenna. You can't just transmit like that. Either my amplitude should be very high that it will directly reach to you. Then there is no need of modulation. I just simply throw a large amount of power to you, but that is not always possible. As I said, I have a limited range, how much at high volume I could speak. Similarly, when we design a system or a transmitter, there is a limitation on the transmitter, how much power it can transmit, because finally it is related to an active device, and the active device that we used is an amplifier or something which in turn uses a transistor, and this transistor is in turn uses junction, and because of the junction sizes and so on, you can transmit only a small amount of power. And also you can amplify to a certain extent. You can't go on amplifying it again and again and again. So how to transmit a low frequency signal to a larger distance? So what we do here, if I directly transmit it, which is not possible, as I said, I can't throw up large volume, large power. So I need some sort of an antenna. And antenna size or any other size of a system is related to the wavelength. And wavelength is nothing, it is inversely proportional to the frequency. I'll be writing all those things when we talk about it, but I'm trying to make you understand. So if my voice signal is at a very low frequency, which you've seen, few kilohertz and so on, and because of this, my wavelength at these frequencies is very high, something like kilometer, because frequency is very small in kilohertz. So your lambda or wavelength is very high. Lambda is equal to C by F. I will be writing to you all those things when we talk about it. So just listen. So I need to carry an antenna kilometer long with me. And similarly, as a receiver at the other end, you also need to carry the antenna of almost same size, 25 kilometer, which is impossible. So this is my low frequency signal, is an intelligent signal or a message signal. We normally in communication, we use the word message. Okay, so sometimes when we write VMT, that means it becomes a message signal. In the previous one, I have written as VT, but some people write as VMT. That means a message signal or something like that. Okay, so if I transmit this low frequency signal, I need to have a very large antenna with me, some 25 kilometer long, and similarly, the person on the other side should also have a large antenna to receive that signal, which is impossible. Why? Because frequencies are small, wavelength is very high, and the size of the antenna is related to the wavelength. Now here, if I use a high frequency signal, which is also what we have written in here, a carrier, and on this carrier, if I put my message signal, okay, then because of the high frequency, my lambda is small, the antenna size becomes very small. So just take an analogy, and this analogy is my analogy, you will not find in any of the books. Suppose a child has to cross a road. If a child has to cross the roads on his own, it will be disastrous. Am I right? So child is my message signal, which has to go to the other end of the road. So child is going from one side of the road to the other side of the road. So child becomes my message signal, intelligent signal here, because that is his aim. Okay. Now, if he crosses this on his own, it will be disastrous. He may meet with an accident. So it is the same thing. If I try to send my low frequency signal or the speech signal or the voice signal or the intelligent signal, which we normally call as message. So message is used to intelligent signal or low frequency signal directly. It is impossible. It is disastrous. Either I will choke my throat or something like that. But if I carry that child, say an elderly person, carry the child and make them cross, we understand that it is totally safe. So similarly here, I override my low frequency or the message signal on a high frequency or carrier signal, and then it carries the signal. The advantage I'm getting is now my modulation, now my antenna size becomes very small. It has become so small that even my mobile phone antenna is sufficient. Okay. Because when I'm speaking on a mobile, I'm speaking at a voice frequency, lower frequency. and you are also hearing or speaking in the same frequency. But what is going on here is it is going through as a signal which is ridden over a high frequency of carrier signal. Carrier means like an elderly person is carrying the child and crossing the road, it is safe. So same way in the modulation here, I'm actually I'm actually carrying the signal. And then I leave the signal. So when we are doing this, how to ensure that it is the same child I'm getting? See, now you understand that many children will be crossing, or many children will be getting crossed by the carriers, okay, elderly person. So which one is which? So for that, we change one characteristic of the signal. And which the characteristic is of which signal is the high frequency or the carrier signal. We'll understand also slightly mathematically. It is not very difficult mathematical concept, but it will make our concept very clear. So if I change the characteristic, any one particular characteristic of my carrier frequency, it could be frequency, amplitude, or phase, I will be able to modulate it. So modulation means changing one parameter of a high frequency carrier. So as I said, there are three parameters of a signal: frequency, amplitude, or phase. So I could change either the frequency or the amplitude or the phase. It is just like I'm putting some sort of a marking that this is the frequency I'm changing, so that when the children crosses the road, I know which child is which. Okay, so here also I should be able to demodulate the same thing or detect the same thing at the other end. Okay, so one of the parameters I need to change to ensure that the right child is cross the road and one can identify there. So you have to demodulate. So I carried the child, cross the road, and then put the child back on the ground. So that's what we call the demodulation. So modulation is to change, and demodulation is the reverse process of that. I have to finally come back to the same original position. Same child has to come, or the same signal has to come. So this is what we call the modulation, and the other parameter when we do at the reverse of this is what we call the demodulation. And it is the reverse of demodulation. So what we do at the modulation, we do the reverse here, and that becomes a reverse of modulation. We'll understand slightly mathematically, and then you will understand slightly better. Now, demodulation means it is also called a detection. Okay, because when so many child crosses, whose child is supposed to be there at the, so that is the particular detection word, and that's something what we call the modem. If you use this word quite often, modem, we all have modem in our homes. What it means, it is the same thing: modulator, demodulator. So they go together, and this gives rise to what we call the modem. You can't simply modulate the signal and just leave it. You have to demodulate it at the other end, detect, so that you get the original signal back. How to demodulate? We have a device what we call demodulator. What goes inside that? We have to understand that. How to modulate? We have a device called modulator, and we have to understand. And what parameter I can modulate? I can change a fixed signal. It is either the frequency, which is called the frequency modulation, or the amplitude, which is called the amplitude modulation, or the phase, or it's called the phase modulation. So modulation, if I have to make you understand again in a better form, a message, which is a low frequency signal or a intelligent signal, what we call, but we use the word message quite often, like my voice signal, being at a low frequency, I need a large antenna for that, because the wavelength is very large and the size of the antenna related to the wavelength, which is impossible. So I use a carrier frequency, which is at a very high frequency. Now that carrier frequency rides, this message signal rides over the carrier frequency. It is called a carrier or the high frequency. So carrier and message go together. Low frequency and high frequency go together. So we normally use the word in modulation in most of the books as carrier and message signal. Intelligent signal is message. Carrier signal, so carrier and message are the two words that we are going to use quite often. But as I said, I will put it here. Carrier is a high frequency and message is a low frequency signal. So which child is taken by which carrier? I have to come and know at the other end. If somebody is like that, that particular child goes to some other people and difficult to identify there. So I put some characteristic on me, some tag. But that characteristic in the high frequency carrier could be one of the parameters of that carrier signal. They are all carrier signal. Okay. And the signal has three parameters: frequency, amplitude, or phase. So I change my frequency, or I change my amplitude, or I change my phase. Then it gives rise to three forms: frequency modulation, amplitude modulation, phase modulation. Okay. Amplitude modulation we start with. Frequency and phase modulation, if you see the frequency and phase, if I see this definition of my analog signal, which in this slide, frequency and phase are part of sine. So amplitude modulation is in one category, and frequency and phase are part of the sine, within the sine bracket. This is called the angle modulation. So sometimes we say amplitude modulation, where I'm changing with the this amplitude part. It is becomes the amplitude modulation or the linear modulation. And this part, when I'm changing either the frequency or the phase, becomes part of the angle modulation, because this is something like an angle, sine of certain angle, and frequency and phase are part of that. So we put both the things in one category. All those things I'll be writing. No need to just trying to explain right now. So angle modulation comes in two categories: phase and the frequency modulation. So we'll start with frequency and amplitude modulation, then angle modulation, which consists of two categories: frequency or phase. So I need to be identified by certain tag, and that tag, some change I have to do in my characteristic, because the same carrier could be there. So let's see how I go for that. Like an example of an orchestra. In orchestra, several instruments are there. Several musical instruments are playing. Each is playing at a different frequency. And they all need to be simultaneously transmitted. You can't say that I will first play with tabla, and then I play with flute, then I play with harmonium. No, all have to be simultaneously getting transmitted. And once they are transmitted simultaneously, you need the carriers for them, because they are all the low frequency signals. And then how to detect them at the different stage, we need to do certain changes in our carrier frequency, so that they could be identified, and then they could be got back to the original position by what we call a demodulation or the detection. So modulation is a must. You can't simply transmit the signal just like that. When I'm speaking through my mobile phone, which is getting transmitted through a tower to your mobile phone or laptop or something like that. So your antennas are involved, your modulation process is involved, your demodulation process is involved, everything is involved, and then you are listening to my original voice signal. It is not a digital signal. It is the same analog signal which I'm speaking, you are listening to that. So this is a simple, and this is an instantaneous. That means, see, the word instantaneous is very important. If I write it here, put it in the red one, instantaneous, at any particular instant. It changes in accordance with the message signal. That if my message signal is low, amplitude, because as I said, it is a sinusoidal signal. Sometimes amplitude is high, sometimes amplitude is low, and so on. So it has to be in accordance with the amplitude of the message signal. So if my amplitude is high, the corresponding parameter of the carrier should also be high. That means corresponding amplitude. If my amplitude of the, in accordance with the, I would say, amplitude of the, I use the word here, amplitude of message signal. My frequency could be high if my amplitude is, or the message signal is high. My phase could be large if my amplitude of the message signal is large. My amplitude of the carrier signal is large if my amplitude of message signal is large. So the three parameters which I'm changing of the carrier vary in accordance with the amplitude of the message signal. It is always with respect to the amplitude, but the parameter, which could be either the amplitude frequency, or phase. They could be changed. So we have three forms of modulation. So my amplitude modulation is defined where the amplitude of the carrier is varied in accordance with the amplitude of the master signal. I will write all those things. Frequency modulation means where the frequency of the carrier is changed in accordance with the amplitude of the master signal. There always it remains the same, but it could be one of these. It could be one of these to give rise to three different types of modulation. That is the amplitude modulation, frequency modulation, and phase modulation. Frequency and phase part of that angle, it is what we call the, sometimes we call that the angle modulation. So analog modulation is a continuous wave modulation, as I said, and it has two categories: frequency modulation, phase modulation, and other thing. Now here, what is the need? Or I think that will start in the next lecture, but just trying to basically understand. So that is one advantage I'm getting. I will put it in all those things in detail in the next one. Also, modulation allows multiplexing. So sometimes we use the word multiplexing also quite often. What is this multiplexing? So I just introduced these terminologies today, and then we'll make you understand in a big way in the next lecture. So your modulation allows multiplexing, especially with regard to the frequency and time and so on. So we could have time division multiplexing, or frequency division multiplexing. This is what we called TDM. This is what we call FDM. What is this? I will explain to you. So basically, why do multiplexing? Because sometimes, as I said, we need not transmit only one signal. Like in an orchestra, we need to transmit multiple signals on a common channel, and that is what we call the multiplexing. So modulation allows multiplexing. And why we need multiplexing? For it allows simultaneous transmission of many signals or message signals here over a common channel. Okay. That means if my voice frequencies are from 300 to 3400 Hertz, as we have seen here, that is my voice frequency band. So there are various, I may be speaking at a larger pitch, smaller pitch, somebody else also along with me is also speaking at slightly different frequency or time or something like that. And we need to transmit simultaneously. That is what we call demultiplexing. So frequency division multiplexing is basically what we do here. We put each signal on a different carrier frequency. And time division multiplexing, which is basically more related to the pulse modulation. So basically we used in a different time slots. So what we do here, I have to transmit many signals simultaneously over a one channel at a particular instant. So modulation is nothing, multiplexing nothing, it is an extension of modulation. Modulation allows multiplexing. So what we do here, either I can put different message signals which I want to transmit in different time slots. That is called the time division multiplexing. Or I assign a different carrier frequency for each of them, like we do in an orchestra, so that it was possible. And the SS techniques to do this is what we call in world is using quite often, multiple SS. So it is nothing, it is a way of doing the multiplexing, multiple SS. So we could have TDMA, we could have FDMA, frequency division multiple SS. Okay, so these two words denote your multiple SS. And something when you are using a mobile phone, we talk about CDMA, which is called the code division multiple SS. Now this has become very popular, especially with the Reliance when they started. Your GSM and everything is TDM based technology, which you'll understand slightly later. So here what we do, we assign a different code. Now code B, if there are very few users, I could define a code in terms of 0111000011 and so on. If I have many users, I could have a 4-digit code, 8-digit code, 16-digit code, 32-digit code. So the advantage of CDMA is that you can transmit many things because you can assign a different code. But within a frequency range, you can't assign many frequencies. But that is also possible. I can define 10.2 kilohertz, 10.3 kilohertz, or even 10.25 kilohertz, and so on. But there is a lot of interference could be possible because they are very close. And time is also 1 by of frequency. So code division multiple access, that means you assign a code. To one same high-speed signal, I assigned a code 00001. Somebody else, I will assign a code 011111, or something like 010101. So that depends. So code division multiple access, you must be hearing these techniques, GSM, CDMA, and all those things. So CDMA is like a code division. I assign a code for them. TDMA and FDMA is the frequency and the phase. So multiplexing is an extension of the modulation. If modulation is possible, then modulation only will allow the multiplexing. Okay, because you are carrying over different frequency carriers, you are carrying over different time slots and so on. So this is the two terms that I want to make it clear: modulation, demodulation, and multiplexing. To understand this thing much better, and the advantages why we do modulation. Only one advantage we have seen, that is the antenna sizes. We have to reduce a lot. Is reduced a lot when we do modulation, unlike if I directly transmit. So that we'll understand slightly in a mathematical way, simple way, because sometimes people get distracted. Oh, a lot of mathematics. It is simple maths to understand this modulation, which we'll do in our next lecture. So I stop it here. Any doubts? Let me see in the chat box. Someone microphone is on. Yes, please make sure that this summit should not take place. Otherwise, yes, please. Question.
Can you please provide drive link of these lecture slides?
Sure. See, I am saying you again and again. I yet to get the list because registration last date was yesterday, add and drop and so on. So once I get that list, I'll form a group and all my previous lectures. In fact, last time also I tried to do video recording, because of which something got disturbed for 10 minutes or so. I will try to do live recording also if possible, because live recording requires a lot of bandwidth. But all these things, what I'm speaking, I am also writing. And I'm also saying that no need to take any other book. These notes are more than sufficient for you. I'll be doing multiple examples or one example, but it is very clear. It will clear the concepts. So just rely on my notes. I understand that even if I prescribe books, it will be difficult for you to assess sometimes. Yes, but then many Google slides and everything is available to you. So just refer to my notes, the PDF files, which I'll be posting you maybe in a week's time. All the lectures, I've got all the files with me. Nothing to worry. The previous 2 lectures and this lecture. And I will be sharing with you maybe by the moment I get the list of the students. I don't know what is the section B. It is going to be rearranged depending upon the registrations. Though I have defined section B, what has been defined. Okay, but I'll put these notes for you. Nothing to worry about that. Okay.
Okay.
Any other question related to technical? Otherwise, in the next lecture, you can ask me at any time. You can disturb me and we can clear the doubts. So I stop it here. End the lecture, save this file as a PDF file, and let you know. Okay.